This presentation is about use of primary geodetic data for the identification of some local deformation patterns. And I would like to present you some results from which come mainly from my PhD student Ilias Lazos' work, and concern these issues. First, let me say a few things about what our thinking is. I mean, we know since several years that GPS data and GPS information show very reliably the displacement pattern for the broader area of whichever study area we are dealing with. For example, we are well aware of the counterclockwise movement of Anatolia and the change in direction. You see here a compilation map of several authors for Eastern Mediterranean, and also from several studies for the Aegean area. So this general pattern is well established, and we know that this is the case. But sometimes we need to look more carefully into specific areas. For example, in this map, you can see some smaller displacements due to the movement of the part north of the North Anatolian Fault, which, however, cannot be analyzed in detail and give us specific results. So in this work, we try to dig into the data and find information, try to find information at least about straying parameters that can describe the actual, the ongoing actual deformation, not always expressed as displacement, but it can be expressed as deformation. For this, we used a time series of a continuous time series of for 7 years, using data from 159 permanent GPS stations. You can see here the distribution of those stations in the mainly in Greece, but also in some stations in the neighboring areas. And I will come back later to this map at the end of my presentation. Several networks, we used information and data from several networks, and we tried to solve the data using the ETRF 2000 reference frame. So what we did is that we used those data from 7 years, 2008 to 2014, and these were continuous time series, meaning that they were time series covering 24-hour operation of the stations, and all the measurements were taken every 30 seconds. So you can see that this is a very big, huge amount of information, of data. For each station and for each specific measurement, the model, the information that we got from the model was the velocities, north and east velocities in the two axes, north, south, and east, west, the vertical velocity, and the component errors for each one of those velocities. To use these measurements, we discarded the vertical velocity because you know that vertical velocity is not very well expressed in GPS and measurements. So we worked with east and north velocity together with their error margins. In order to process the data, we used a quite simple methodology, which I would like to explain to you briefly. This methodology is a triangulation of sites and a triangulation of respective measurements. It all starts with 3 neighboring stations and the corresponding east and north velocity vectors, from which then we can calculate the total horizontal velocity, which is the component of those 2 vectors. So for each site, we can have this kind of configuration with the horizontal velocities that are produced by this process. The next step is to find the center of this triangle, and this is why it's called triangulation, which we consider that it represents the status of the entire area within this triangle. So for this, the centroid, we draw a circle with the center of which is the centroid of the triangle, and then based on the vectors, on the component vectors, we move the center of this circle, and we move the triangle corners accordingly to the vectors. This is an automated procedure which leads to the deformation of the circle. This deformation shows us, the axis of this deformation shows us the main deformation pattern in the area. If we then translate this ellipse to the initial position of the centroid, we have the final product, which is the centroid of the deformed triangle and the ellipse that shows the actual deformation pattern in this point. So this can of course be automated, but it needs a lot of attention from the user and some critical reviewing, because one has to be very careful about choosing those 3 triangles and applying, at least what we did is that we applied geological data, geological information, so that we can have triangles that have a meaningful geological, that show a meaningful geological situation and an active tectonic situation. That is, triangles that probably are belonging to the same block, or that have some faults crossing the areas, etc. And this is the final product, these 2 axes. And of course, any structural geologist can understand that if the difference between those 2 axes is large, then the deformation pattern in each in that point is large. If the difference between those 2 axes is small, then there is not much deformation. So by using, let me go on, by using this data and combining the information, we estimated some parameters for the specific point, which is again by definition it is representative of the area between the 3 stations. And by using those parameters, we interpolated missing values through kriging. So what were the parameters that we extracted from this process? Mainly the maximum and minimum horizontal extension. I'm going to use these letters later on, so to save some space. The total velocity of this point, the maximum shear stress, and the area strain. And I will explain to you later what each one of these means. Apart from these parameters, a few more were extracted during this process, but they are not relevant, or at least they are not very useful at this presentation. So I'm going to show you two examples, one from central Greece, the Corinth Reef system, and one from northern Aegean. They both are two very different geotectonic environments. Corinth Reef system is a well-known complex graben system with normal faults bounding both of bordering the Gulf from both sides. So in this area, we used information from 14 permanent stations, and the resulting calculations were done by using 26 different triangles between those stations, as well as different centroids, 26 different centroids. So what is, let me just start by the maximum horizontal extension. These are the results of this analysis, and it shows that there is a difference in various parts of the Gulf. They are consistent with this general map. This is by Hollenstein et al. 2008, which also shows an anomaly in Corinth Gulf. However, this analysis shows this deformation in more detail. Maximum horizontal extension is equivalent to the maximum extensional axis if we are talking with structural terms. And again, we see that these, if this is the quantitative information, these two areas show show more extension. They are more, let's say, active areas in respect to the others, although one could argue that all faults in this area are active. Again, the next parameter is the total velocity. Again, we see here a pattern that is consistent with the known models, but one can see that values north of Corinth Gulf are generally smaller than the ones south of the Gulf. This is consistent with the general geologic situation in Peloponnese, which is this area here, where the geological observations show that extensional deformation is much stronger by exposing lower tectonic units. Again, the quantitative results, which are not very important at this point. However, the maximum shear strain shows a quite interesting result. These are the areas of the centroids with the maximum shear strain in various areas. Those three are consistent with the maximum extension that I showed you before. However, there is one area here that is not represented in any map. You see here, this is the the part of CREDAS, the Greek database of seismogenic sources, and there is no fault in this area. The reason that this area shows such a large shear strain is because in 2008 a strong earthquake happened and caused the deformation of this area, despite no fault reaches the surface. Up to then, there was no known fault that reached the surface. Again, the same, the area strain is consistent with the maximum extension in these areas, but also you see here the area strain that corresponds to this event. Let's move on to the conclusions for Corinth Gulf before we move to the next area. There is this shows a differentiation, a local differentiation of values. Some of them, most of them are consistent with the general model. However, if you dig into the data, you can see that there are some smaller areas of specific interest and especially the 2008 event is completely changing the overview of the area. And another example from North Aegean, which is well-known area. This has some interesting features. The main is that it is mostly covered by sea, so the distribution of stations is not very good. Again, with the available data, there were 32 permanent stations and 404 centroids, again using the triangulation method. And this shows again some interesting results. I'm going to go through a bit quickly because time's running out. The maximum and minimum horizontal extension, as you can see from the magnitude of the arrows, in most cases is consistent with a known structural pattern. However, there are some areas like this area in Thrace where the deformation of there is a large deformation without having any large known active faults. And the total velocity again shows quite interesting result. The area south of the North Anatolian Fault is as expected, moving with larger velocities. However, there is significant movement again from north to south in northern Aegean, and there is an area north of the North Anatolian Fault where there is again southwestward movement with all the uncertainties because this is the sea. The same again with maximum shear stress. It is concentrated in some well-known areas that we expected to have a shear strain. And again, there are some areas like here in Thrace or in central Greece where the shear strain is larger than expected, and probably due to local tectonic conditions. The same goes for area strain. Again, the same results for the large structures of the area, and again some localized areas that are undergoing deformation without any visible any large large known active fault zones. And let's close this section with a few conclusions. That it is the main deformation type is shearing, because we know that it is associated with side slip folding. However, in some points we have, as mentioned, pure dilatation. So to conclude, if we take the bigger picture, and this is these are the results for the entire area, we can see that there are various parameters shown in areas of well-established fault zones, but there are also some local, let's say, islands of deformation in areas with no large faults or small faults that we did not expect. So the same goes for shear strain and area strain. So we think that this can be a good way to have an indication of ongoing deformation in areas outside the main zones. But one problem here is that this was let's say a test run of 7 years. We need longer time series, but more importantly, we need information from more stations, especially from Turkey, so that we can have more reliable results for the entire area. And one idea is to have this automated so that we can establish a continuous monitoring system that can show active deformation in real time. So thank you for your attention.